Alright, so this is robotPaths. Let's take a look here. Alright, the problem is a robot located at the top left corner of an n by n grid is trying to reach the bottom right corner. The robot can move either up, down, left, or right, but cannot visit the same spot twice. How many possible unique paths are there to the bottom right corner? Well, let's see. We got some helper function here. It's going to make the board. As you see, it's going to construct it. It's going to push a Boolean value into an array within an array. So that's cool. We can access that with, you see, with toggle piece and has been visited. You can access it with this ij. That's going to get to the piece on the board. So let's do this. You know, we see Optimus Prime here. He wants to get back home. Let's help him out. So just for some visualization here, this is what the grid is going to look like. If we toggle piece 0, 0, I being 0, j being 0, it's going to be the top left corner, and we want to get to the bottom right corner, and that's going to be with the board length being n minus 1, n minus 1. So keep that in mind. That's how we're going to refer to all of the pieces in our grid. So first, let's set this thing up. We want the function to be called robotPaths, of course. We want to declare a variable called paths count, and we want to make a board with the board constructor and the helper function. That's cool. All right, and then we're also going to make a find paths function. And for now, let's just assume we're going to be doing some fancy stuff in it because it's going to be a recursive function. We definitely need recursion for this kind of problem. So let's deal with that later. And then we know within our robotPaths function, we're going to want to invoke that recursive function starting at the top left corner, and then return the total paths count, which will be some number, hopefully other than 0. All right, so let's recurse. So first we got to set up our base case, and our base case is going to be if I is equal to n minus 1 and j is equal to n minus 1. We want to increase path count and return immediately. It's returning early. And remember before that grid where the the bottom right hand corner was n minus 1, that's basically what we're referring to with this base case. And the base case is basically saying, you know, if you get to that spot, that's a path. You know, count the path up, return, we don't need to recurse anymore. So let's go on to the next one. So we see our base case is there still. Cool. If a robot reaches the edge of the grid or the current spot has already been visited, return. Okay, we can do that. So we have this kind of this long expression here, but just look at it. It makes sense. If I is less than 0, so you kind of, you know, it's on the, if I is kind of the horizontal spaces, if it's on that side of the grid, or if it's grid on the other side, or if j is less than 0, or j is greater than the width of the board, or we see that it's been visited before, we want to return early. So that makes sense, right? And then we have our else function, which is coming soon on the next slide, which is this slide. And this is what we want to do for else. We have these two, one being a base case, and the other being another case where the spot is such where we don't want to keep doing recursion on that spot because it's either been visited or it's outside the board. So for this, on the else, we want to first toggle the piece on the current spot, and then check the paths with our function recursively for both all the directions, right, down, left, up. You can see with I and j, that kind of makes sense, right? I mean, we've been using I and j as our two-dimensional vector system for, even though it's an array within an array, we use it as kind of like xy coordinates. So we want to check all those. With every time we invoke find paths, it's either going to recurse or it's going to hit the base case. And if such, we're going to want to toggle the piece back. So that's what we're doing at the end. And that's it.